So hello everybody. It's a great pleasure to be here today at this new Rome Joint Astrophysics Colloquium. The Rome JAC is a joint initiative of the Physics Department of the University of Rome Tor Vergata, the INAF Astronomical Observatory of Rome, and the INAF Institute for Space, Astrophysics and Planetology. It is a great honor today to introduce Professor Rolf-Peter Kudritzki. Professor Kudritzki obtained his diploma in physics in 1971 and PhD in astronomy in 1973, both from the Berlin Technical University. Professor Kudritzki has had several prestigious academic and research appointments. From 1982 to 2000, he was professor of astronomy and director of the Institute of Astronomy and Astrophysics at the Munich University. From 1999 to 2000, he was Dean of the School of Physics at the Munich University. From 1990 to present, he is a scientific member of the Max Planck Institute for Astrophysics. From 2000 to 2010, he was director of the Institute of Astronomy at the University of Hawaii. From 2011 to 2017, he was astronomer with tenure at the Institute for Astronomy at the University of Hawaii, and from 2017 to present, he is astronomer emeritus at the Institute for Astronomy at the University of Hawaii. You can see that he has a long and strong link with Hawaii. From 2012 to present, he is founding director of the Munich Institute for Astrophysics and Particle Physics at the Munich University and Technical University of Munich. And from 2018 to present, he is also professor at the Munich University Observatory. He has received several awards, such as the 2006 Highly Cited Author from the Science Citation Index. In 2009, the Karl Schwarzschild Prize of the German Astronomical Society, and also in 2009, the Humboldt Prize of the Alexander von Humboldt Foundation. So the title of today's presentation is The Brightest Stars in the Universe as Extragalactic Probes of Cosmic Abundances and Distances. Please, Professor Kudritzki, the floor is yours. Thank you.
Okay, thank you for the kind invitation to speak in your colloquium, and thank you for the introduction. I will try to share the screen. Please let me know whether it works. I think it does.
Yes.
Okay, so as you already said, the title of my talk is The Brightest Stars in the Universe, Extragalactic Probes of Cosmic Abundances and Distances. And essentially the talk is about extragalactic stellar spectroscopy and how to use this type of stellar spectroscopy to determine distances to galaxies, but also to determine chemical composition of the stars in these galaxies, and in this way to learn something about the formation and evolution of galaxies. And as you certainly all know, galaxy evolution is a tremendously complex process. I show a high-resolution animation here on the left, how the gas in a galaxy evolves as a function of redshift, and on the right side, how the stellar component of these galaxies evolves. And just by looking at these simulations, you see already what a violent process this is. You have gas inflows. The gas inflow leads to star formation. Star formation leads to stellar mass growth. Stellar mass growth then leads to chemical enrichment, but also to galactic wind outflows. So you always have a competition of gas inflows and outflows. And then you have also the merging with the neighbor galaxies, which contributes to the evolution of these galaxies. And as I said, when you look at this, you get an impression to really physically describe this process in a somewhat simpler way, so that you have a big picture about galaxy evolution is almost hopeless, because it looks so complicated and so many processes are happening for which you don't know the details. So that's the one side, but then on the other side, when you look at the observations, you find some striking very simple relationships. So one of them, and that's a key relationship for my talk, one of them is the mass-metallicity relationship of galaxies, originally found by James Lecuyer and Manuel Peinbert in a publication 1979. But then later, with the big surveys going on, the key paper has been the paper by Christy Tremonti and collaborators in 2004, where she analyzes the emission lines of 50,000 Sloan galaxies and comes up with the mass-metallicity relationship, which I show as a figure here. It shows logarithm of oxygen abundance as a function of the logarithm of the stellar mass in a galaxy, and you see a tremendously tight relationship. And looking at this, after these complicated animations that I've shown before, you get the feeling this is some kind of a Rosetta Stone to understand galaxy formation and chemical evolution. And this mass-metallicity relationship does not only hold in the local universe, it extends to higher redshift, as you see from this diagram here. It goes out to at least redshifts like 1.5, again observed from emission lines of galaxies as an evolution of this mass-metallicity relationship, but clearly these very simple relationships do exist. And of course, that sort of asks for theoretical work to understand how galaxies evolve and how this evolution leads to the mass-metallicity relationship. But before one starts to do that, one really has to be careful. I go back to the relationship in the local universe, and now I overplot three numbers, namely the metallicities of the inner Milky Way, the Large Magellanic Cloud, and the Small Magellanic Cloud. And very strikingly, you see, these three numbers don't agree with the Tremonti et al. Mass-metallicity relationships. They are systematically off. And the reason for that is how these metallicities for the galaxies were determined. They come from strong nebular emission lines, and the method to transform the fluxes of these emission lines into metallicities is called the strongline method. And these strongline methods depend heavily on the calibrations that you use. And in the key paper in 2008, Lisa Cooley and Sarah Ellison used the same set of 50,000 Sloan galaxies, the same set of emission lines, but applied 10 different calibrations of the strongline methods to determine oxygen abundances from these strong emission lines. And they came up with 10 vastly different mass-metallicity relationships. And that is really not a small effect. And of course, if you want to come up with a theoretical interpretation of these observations, then you need to figure out which of these mass-metallicity relationships is the correct one. And that's where the stars come in, because I hope I can convince you during my talk that the information about chemical compositions in relatively distant galaxies outside the local group that we get from stellar spectroscopy is more precise. And the objects that are using for this purpose are supergiant stars. They are beacons in the universe. They are the brightest stars in visual and infrared light, and I use two different types. I use the blue supergiant stars, which you find in this pink rectangle here in the Hertzsprung-Russell diagram, and I use these are hot stars with effective temperatures between 20,000 down to 8,000 Kelvin, and then I'm using red supergiant stars with temperatures about 3,500 Kelvin, cool stars, and both groups, and I will determine metallicities from these two groups of stars and compare them. That's a project I've started quite some time ago when the multi-object spectrographs became available at the big telescopes, and I've been using the Keck telescopes in Hawaii for that purpose, and the ESO-VLT, usually for one galaxy outside the local group like M81 or M83 or something like this. I need 2 to 3 nights per galaxy of multi-object spectroscopy. And so far, something like 50 plus nights have gone into this project. Just for the cosmologists among you who don't know much about stars, this is how supergiant stars look like in our own neighborhood. Alpha Orionis as a prototype for a red supergiant star, and Rigel as a prototype for a blue supergiant star. And that's how these stars look like at a distance of almost 7 megaparsecs in the galaxy NEC 3621. And you see them here encircled and squared, and they stick out from the background of these galaxies because they're so tremendously bright. And it's easy to find them from color magnitude diagrams. And per galaxy, star-forming galaxy, you find a lot of these supergiant stars. And because they are so bright, you can do spectroscopy, and this in the middle here of these 3 spectra, the middle spectrum is a spectrum in this galaxy 7 megaparsecs away, compared with 2 galactic template spectra. That's an A supergiant, which I have here. And the only message from this diagram is that the quality of such a spectrum in a galaxy 7 megaparsecs away is comparable to the quality of the spectrum in the solar neighborhood. Of course, that is low resolution spectroscopy, typical resolution as the Keck-Elder spectrograph or the Force spectrograph, something like 5 angstrom resolution, but that's good enough to determine metallicities with a precision between 0.1 dex or plus minus 0.1 dex or 0.05 dex, as you will see in the next slides. So spectroscopy of individual stars is possible to determine their temperatures, gravities, and chemical composition. That's just an HST image of blue supergiant stars in this galaxy 7 megaparsecs away. And it shows you how bright these objects are and how they stick out. They are ideal sources for chemical abundance studies and distance determinations. You don't have to worry about contamination with the light from neighbor stars because these objects are so tremendously bright. Now, in order to determine chemical composition or metallicity, you need model atmospheres. And with my group in Munich, already a long time ago, we have started to calculate these model atmospheres. And now, in the meantime, we have tremendously advanced model atmospheres for hot stars with hundreds, thousands of lines of all the elements calculated in very detailed non-LTE, taking into account the effects of departure from local hydrodynamic equilibrium. And in this slide here, in this figure, I show just a small fraction from the spectrum of a blue supergiant star, just 100 angstrom, and it shows you the presence of many iron, titanium, and chromium lines. Spectra are calculated in this resolution of 5 angstroms, and they are plotted as a function of metallicity, where Z in brackets is metallicity on a logarithmic scale with metallicity in units of the solar metallicity. And what I show here in the plot is the metallicity dependence of these spectral lines from 1/20th solar metallicity up to a factor of 2 above solar. And you see there is a strong signal on metallicity in these spectral lines. And that's the reason when I use not only spectra in this small range of 100 angstroms, but over the full spectral width from the near UV to the visual and sometimes also to the near infrared, then I can obtain very accurate information about metallicity and determine the metallicity of these stars with a precision of 0.1 to 0.15 dex. And these are typical fits of the spectra. You see all these different lines, iron, chromium, etc. And so we get very good information about chemical composition. That was NEC 3621 at 7 megaparsecs. Another example of more recent work with Fabio Guisolin and Miguel Obanera is our work on NEC 2403. Again, you see all the individual objects, how they stick out from the images, and then you just do multi-object spectroscopy on these objects and fit the spectra and determine metallicities. We can do this for blue supergiant stars, and I've just shown these examples, but we can also do this for the red supergiant stars, which you see here in this reddish rectangle, and for that we use multi-object near-infrared spectrographs like CMOS at the ESO-VLT or MOSFIRE at HEC. And just another example, NGC 300 at 2 megaparsecs distance with red and blue supergiant stars, and that is a typical fit of J-band spectra of red supergiant stars in this galaxy, and how we determine metallicity. You see, in this particular case, we are not fitting ionic lines of iron 2 or chromium 2, etc. Instead, in this part of the J-band spectrum, we have a whole lot of atomic iron, titanium, silicon, and magnesium lines, and that's where we get the metallicities from. Again, from detailed non-LTE calculations. These non-LTE calculations have been carried out by Maria Bergemann and her group, and she is part of this collaboration for red supergiants. And this next slide here is very important in view of the discussion of potential systematic errors, because before I had criticized the work on H2 regions and how uncertain it is to determine metallicities from H2 regions. Of course, also stellar work has systematic errors, but we know, of course, from the work in the local universe, where we have applied all these spectroscopic diagnostic techniques already, that the systematic errors are usually not much larger than something like 0.1 dex, and this diagram here confirms it. It shows for the galaxy NGC 300 a plot of metallicity of the individual blue supergiant and red supergiant stars as a function of galactocentric radius down here. Plotted as galactocentric distance of the objects in units of the isophoto radius. And you see, of course, the abundance, the metallicity gradient in this spiral galaxy. That's a well-known effect in spiral galaxies. Metallicities in the interior are higher than in the outskirts. But what you also see is there is no systematic difference in metallicity between blue supergiant stars and red supergiant stars, and the two regression curves, which are plotted here, agree within less than 0.05 dex. And that's very reassuring, because blue supergiant stars are hot stars. You need model atmospheres and radiative transfer and non-LTE for hot stars and ionic spectra. And red supergiant stars are cool stars, so you need model atmospheres for cool stars and for atomic or molecular spectra. And yet, although these objects and the properties of the atmospheres of these objects are vastly different, we have excellent agreement, and that sort of reassures that the systematic errors that I have in this stellar work are small. We can also use the integrated spectra of superstar clusters for metallicity studies. Superstar clusters, as you know, are dense, massive aggregates of young stars in star-forming emerging galaxies. These are very young clusters with masses between 10 to the 5, 10 to the 6 solar masses. And it turns out, when you look at the J-band spectra of these objects, they are dominated by the red supergiant stars. It's easy to show by population synthesis that, although you have 10 to the 6 stars in such a cluster, the light in the J-band is dominated by the 50 red supergiants, which are in this cluster at any time as soon as it is older than 10, than something like 8 million years. So one can use the J-band spectra of the superstar clusters also to determine metallicities, and we have done this already as far out as antenna galaxies with something like 20 megaparsecs, and have determined metallicities also from the red supergiant spectra of superstar clusters or individual red supergiant stars. Now, when you put all this together, all this work, you can come up with a supergiant mass metallicity relationship of galaxies, and that is shown in this plot here. So here in this plot, I plot metallicities of 17 local universe galaxies out to something like a distance of 20 megaparsecs with the antenna galaxies, and the blue symbols are the data from individual blue supergiants, averaged, of course, over the whole galaxy. Red the numbers from red supergiant stars. Pink is the most recent work on NGC 2403, and you see we get a very, very nice mass metallicity relationship. You can compare this with the mass metallicity relationship from H2 regions, and by this identify the strong line method, which gives the most accurate metallicities from H2 regions. Turns out that is the Pertini and Pagel calibration of the strong lines that comes closest to our stellar work. Of course, one wants to interpret this mass metallicity relationship for galaxies, and I've done this in a recent paper where I developed a relatively simple chemical evolution model, and that's a green curve, which I plot here. And very briefly, I want to sketch how this chemical evolution model works. I call these models look-back models because in order to calculate the chemical evolution in these models, you need the relationship between look-back time and redshift, which I find here in the first equation. Then you need to make an assumption about stellar mass growth in galaxies, and here you assume that all the galaxies evolve along the star-forming main sequences, which you have from observations, and as a star formation rate law, I adopt the law which you obtain from the observed star formation main sequences. The star formation rate is proportional to stellar mass in a galaxy times an exponent delta, which depends on redshift. And with this star formation law, I can calculate the growth of stellar mass as a function of redshift. And that normally in a detailed simulation or a detailed model of evolution of galaxies, that is a complicated part. You need to have a relationship between the gas mass, the total gas mass of cold gas in a galaxy, and the stellar mass. And motivated by observations in the very local universe at really low redshifts, I come up with a relationship between gas mass and stellar mass, which is a power law in stellar mass. So the gas mass at any given redshift of a galaxy is given by the stellar mass with an exponent beta, where beta is of the order of 0.5. And the proportionality factor here is redshift dependent with an exponent equal to 0.4. So that's my key assumption. It's sort of motivated by observations in the local universe, and then it's sort of just simply a guess how this behaves. And then I have checked this in this paper by comparing with detailed cosmological observations, detailed cosmological calculations and simulations, how galaxy evolves. And it turns out that this simple relationship between gas mass and stellar mass captures all these complicated processes of gas infall, gas accretion, and gas outflow by galactic winds. All that simply is condensed in this simple power law relationship. But when you make such a simplifying assumption, then you can write down the equation of chemical evolution for a galaxy, how the metallicity, the mass function of metallicity, Z, changes with an increase of stellar gas mass. That's then a simple differential equation, which I can solve analytically. And as a result, I get this simple analytical formula where essentially metallicity is a function of the ratio of stellar mass to gas mass. That is this, in principle the same as in the classical closed box model, except that I don't make the assumption of the closed box model of chemical evolution, because I have this relationship between gas mass and stellar mass, which is of course different from a closed box model. But with this assumption, I get this analytical solution, and it fits the observations extremely well, as you can see here. But also, when you extend the observations to higher redshift, now using observations from H2 regions, but using the calibration by Bettini and Pagel, which agrees with our work on blue supergiant stars. And then you see that these are the red curves here in my plot, that the look-back models and the red curves fit the observations really well. And so the metal-poor galaxies are the gas-rich galaxies, and the metal-rich galaxies in these mass-metallicity relationships are the metal-poor galaxies in this kind of interpretation, simple interpretation that I have developed. In this last, now, so far I have been using only spectra of individual supergiant stars to determine metallicities, but of course it is also possible to analyze the spectra of the integrated whole stellar population of the galaxies. And for this purpose, in this paper with Jabran Said and Charlie Conroy, we have studied spectra of 20,000 Sloan galaxies, star-forming Sloan galaxies at a redshift of 0.08 up to 0.15. We have stacked these spectra together in different mass spins. So what you see here are spectra of Sloan galaxies of very high mass. These are the upper spectra, and down here are spectra of, that is here something like 10 to the 11 solar masses for the stellar mass, and down here we have galaxies with something like 10 to the 9 or 10 to the 8.5 stellar solar masses. And so these are spectra of different galaxy masses, and in each of these spectrum is practically a stack of something like 20,000 individual spectra. So the signal-to-noise in this spectra is enormous. It's of the order of 1,000 or better. And you can use this to determine average metallicities in these galaxies. And I get this, you know, that the H2 region work gets the metallicities from these emission lines, but I get the metallicities from these little wiggles that we see here. So what you see here in these spectra, that is not noise. You know, these are stellar spectral lines of the integrated stellar population, and I can use it to determine metallicities. And we do that in a very simple way. We say the integrated stellar population that you see here is practically the sum of different bursts of star formation which happened at different times with different metallicities. And we calculate single population spectra of bursts of star formation with different burst ages and different metallicities, and we just adopt the model spectrum then as a linear combination of these different bursts. And of course you have to take into account the reddening of these galaxies as well. And then you fit the spectra with the least square mechanism, which determines the coefficients here of this overlap of the different bursts. And once you have the coefficients, you can use these coefficients then to determine an average metallicity of these galaxies. And I just show an example of this fitting process of the integrated stellar population, which is shown here in red, the model calculations, in blue, the observed spectra, and I show enlargements of different fractions of the spectrum, and you see how nicely the calculations fit the observations, and one can determine metallicities with quite some precision. And as a result, in addition to the results that we had on individual supergiant stars, which are red and blue in this mass metallicity relationship, we now also have these orange data points from fitting the integrated stellar population in these known galaxies, and again with sort of reasonable agreement with the observations. I want to make the point that, of course, with nowadays integral field spectroscopy, well, let me go back again. So these orange points are sort of vast averages of whole galaxies. So the Sloan fibers just put on these galaxies and averaging over quite a fraction of the galaxy, and so these are average metallicities. But of course, with integral field spectroscopy, you can spatially resolve the galaxies and determine, and then you get spatially resolved spectra of surface elements of these galaxies. And of course, you can try to apply the whole population fitting techniques and on these spatially resolved galaxies. And there are several groups now which are doing that, and I'm doing that also with my student Eva Sextel at the moment here in Munich, where we're trying to come up with extinction maps of galaxies, which we have determined from the spectra of the integrated stellar population, but also with determination of metallicity and ages. That is work in progress, and I don't have final results. I have only preliminary results here about extinction, and here metallicity maps of this galaxy, and of course also age maps. As I said, we are still experimenting, and I'm not fully trusting these results, but it has a tremendous potential, of course, in the future, because when you are able to do that for the nearby universe, you can do this also for the galaxies in the more distant universe, because the surface brightness, as you know, is independent of distance. In other words, when it works for the galaxies nearby, you can also produce metallicity maps for more distant galaxies, of course, with lower spatial resolution, but you still would get elements of spatial resolution. Now, let me change gears now and talk briefly about how to get distances from galaxies using blue supergiant stars first. And so why should one be interested, and why in the world would one need an additional distance indicator? That is, of course, and you may have heard about this, because one has more recent work which comes up with more accurate distance determinations. This most recent work has led to a new Hubble discrepancy problem, this time between the Hubble constant determined from the cosmic microwave background and the Hubble constant determined from the distance ladder approach. And that is summarized in this figure here, where the blue data is the Hubble constant values as they are obtained as a function of time from the distance ladder work, and the red result is the result obtained from the microwave background. Of course, there are lots of arguments back and forward whether this discrepancy is a real discrepancy or whether, as usual, people just underestimate the error bars. And with the Mir Institute here in Munich, we had already several workshops on this topic, and it's a really very interesting discussion. But anyway, it is clear that it is very important to determine the Hubble constant with as accurate as by any means possible, not only just simply to determine distances, but also, for instance, to determine the equation of state parameter W of the universe, because as you probably also know, the error that you obtain for W is twice the error that you have for the Hubble constant. So in other words, if your Hubble constant is accurate to 5%, your error in W is 0.1, and that's certainly not good enough to constrain dark energy. So the goal is to obtain a Hubble constant with a precision of 1%. And that, of course, requires a lot of independent, accurate methods to assess the systematics of the individual distance determinations. Now, the perennial problem of extragalactic stellar distance indicators is the metallicity dependence of the distance indicators for Cepheids. That's a long-standing problem, and as you have already seen from my results before, spiral galaxies where you find Cepheids have metallicity gradients. They are metal-rich in the inner regions, metal poor in the outer region. So which metallicities to apply when you determine distances with Cepheids? That's one of the problems. And the other, even more important problem is the perennial problem of dust extinction. Not only is extinction variable, of course, in spiral galaxies, also the extinction law itself and R sub V is variable. And therefore, you need a distance indicator which allows for each individual object to determine independently the extinction value, but also the extinction law. And with supergiants, you can do that because you determine the stellar properties precisely, temperature, gravity, metallicity. Therefore, you know the intrinsic energy distribution, and therefore then you can also determine the extinction law and the reddening while using them. And at the same time, supergiant stars are also so bright that they are not affected by stellar crowding, and so you can use them for very accurate distance determinations. And how can I do that? There is a very simple method which I figured out quite some time ago. On the left here you see a Hertzsprung-Russell diagram with evolutionary tracks, and the blue supergiant stars are in this region here where the evolutionary tracks cross across the diagram at constant luminosity and constant mass. And when you assume that in this evolution from the left to the right in the Hertzsprung-Russell diagram, luminosity and mass are constant, then you realize that a very important quantity, the quantity which I call the flux-weighted gravity, which is the stellar gravity divided by the force power of effective temperature, that according to this evolution along such an evolutionary track, this effective gravity is constant. And it's just a back on the envelope calculation to show that luminosity, since you have a mass-luminosity relationship where stellar luminosity goes with mass to the power of x, then you can immediately show that luminosity is related to the flux-weighted gravity g divided by t to the 4, or when you introduce photometric magnitude, you get the flux-weighted gravity-luminosity relationship, where volumetric magnitude of a star, of a supergiant star, is given by the logarithm of gravity divided by the force power of temperature. And so we have a relationship. In other words, when I observe a supergiant star and determine its gravity and temperature, I know its absolute magnitude, and therefore I can determine the distance. And that is the most recent calibration of the flux-weighted gravity-luminosity relationship done in the Large Magellanic Cloud. That is work I have done together with Miguel Oberneher. That's the relationship which we use now for determining distances to galaxies. And I show a few examples for distance determinations. Two galaxies close to the local group, or in the local group, or close to the local group WRM, NEC 3109. You see the observed flux-weighted gravity-luminosity relationship here and the corresponding fit, which then leads to a distance. That's the other galaxy here, M33, NEC 300 is another example. Again, flux-weighted gravity-luminosity relationship fit. They all lead to a very precise determination of distances to these galaxies, M81 and NEC 3621. Again, very accurate distance determinations. And then NEC 55, M83. And finally, IC 1613, NEC 2423. So in total, we have quite a sample of galaxies already where we have determined FGLR distances, and we can compare, for instance, with tip of the red giant branch distances in this plot here, distance modulus with the one method versus distance modulus with the other, it looks good. But in reality, you have to look at the difference plot. And again, it sort of looks good, but when you look at the mean difference, which is the red dashed line here, you find a systematic offset of 0.04 magnitudes, which, you know, in previous times you would have said that's a great agreement between the two methods. In these days where you want to determine a distance with 1% accuracy, you have a 2% systematic difference between the two methods, and that's a small difference, but it's important in view of the discussion for the Hubble tension. So I'm not saying that I have a Hubble constant from flux-weighted gravity-luminosity relationships, but I'm on my way, and I'm getting closer. And finally, if you give me another 3 minutes, I extend in the very end this flux-weighted gravity-luminosity relationship from just blue supergiant stars to all stars, and I come up with a universal distance indicator of stellar distance. I mean, that's something that as a stellar astronomer we always wanted to have. You know, I take a spectrum of a star, of any star, and from the spectrum of the star I know the distance. And that's a method I introduce here, and you know, this is a plot of evolutionary tracks from Hertzsprung-Russell diagram from 0.8 solar masses to 40 solar masses. And I show 2 types of evolutionary tracks with rotation. These are the solid curves, and evolutionary tracks without stellar rotation. What you take away from this diagram is that stellar luminosity obviously depends on stellar mass, that we know. That's a mass luminosity relationship, L proportional to m with the power of x of the order of 4.5 for main sequence stars. But then, you know, luminosity depends on temperature, and luminosity depends on angular momentum. So it looks a little bit hopeless to determine just simply from a spectrum the distance to a star, but it is not true, as you will see in the next slide. So what we determine from a spectrum of the star usually is effective temperature and gravity. And now, at the next slide, I show a plot where I again plot bolometric magnitude, same evolutionary tracks, but now not as a function of effective temperature, but as a function of flux-weighted gravity. As you know, flux-weighted gravity is gravity divided by the force power of effective temperature. And what you see here in this plot is sort of amazing. You know, that was the plot before. It takes the same evolutionary tracks and just change what I use on the x-axis for this plot. Now I'm not using effective temperature, I'm using logarithm of flux-weighted gravity as it is defined here. And now you see a very tight relationship, because each individual track that you had seen before is now aligned to this kind of curve with a slope in this diagram of 2.5. And in general, all these evolutionary tracks form a very, very nice relationship of bolometric magnitude versus flux-weighted gravity. The sun, by the way, is the red circle here in this diagram. Now, so that's a prediction by stellar evolution theory. And the next slide shows observations where I take accurate gravities and effective temperatures from eclipsing binaries. There is the Dept catalog of 450 eclipsing binaries, and it takes the numbers of these objects and just plots them into this plot. And what you see is an amazing agreement between this extended flux-weighted gravity-luminosity relationship. And that now comprises stars from 0.3 solar masses up to something like 30 solar masses. Not only blue supergiants, also main sequence stars, stars on the way to become blue supergiants. What I'm not including is red giant stars, but everything from the main sequence until the beginning of the red giant phase is in this diagram. And you see, all what you need to do to to determine a distance to a star as determine gravity and effective temperature and applies this relationship, and then you know the distance. And we have tested this in using Lamosse spectroscopy of 2 million Milky Way stars. So that's a collaboration with Hans-Walter Ritz, who is in this Lamosse collaboration. 2 million Milky Way stars with spectra of signal to noise better than 20, low resolution, and those stars have Gaia parallaxes better than 5%. And these are the reddish objects here in this diagram. The green ones we are not using in this comparison because they are on the way to become red giant stars. And now you see the extended flux-weighted luminosity relationship for these Lamosse stars, and there is amazing agreement with relationship, and that means even with low resolution spectroscopy and relatively noisy spectra, as soon as you are able, you determine gravity and temperature just from this extended flux-weighted luminosity relationship. You have a distance indicator which is accurate to 10%. Okay, so that's essentially what I wanted to show you now just for the supergiant stars and IFU spectroscopy, the perspectives with the next generation telescopes such as the TMT and the ELT. For blue supergiant stars, essentially this work can be extended to 30 megaparsecs distance. You can do in the local universe quite significant chemical evolution studies, distance determinations, extinction law studies, etc. For red supergiant stars, the potential is even larger. You can in principle go out to something like 100 megaparsecs and using superstar clusters, even a factor of 10 further out. And we also will be able to study chemical evolution of galaxies with spatially resolved IFU spectra of integrated stellar populations, in principle out to a redshift of something like 1. And I think for a stellar astronomer like me, that's sort of an amazing extragalactic and cosmological perspective. And with that, I want to finish my talk. Many thanks.